Hello world, welcome back to another episode of LeetCode Legends. My name is Brian, and today I got a great question for you. I'm going to go over longest increasing subsequence, LC300, and specifically, I'm going to be talking about the O of n log n approach to this question. If you want to see the dynamic programming approach, I'll link you to another video in the description. Let's start off reading the question here. Given an integer array nums, return the length of the longest strictly increasing subsequence. So given an array 10, 9, 2, 5, 3, 7, 101, 18, the length of the longest increasing subsequence is 4. And that sequence is 2, 3, 7, 101. Quick reminder of what a subsequence is. It's just a set of numbers from the original array that maintain their relative ordering, but aren't necessarily contiguous. So 10, 9, 2 would be contiguous, and it's also a subsequence, but 10, 9, 3 is a subsequence. 10, 9, 101 is a subsequence. 9, 3, 18 is a subsequence. Here we're looking for the length of the longest increasing subsequence. Usually I like to kick things off with some legendary thinking, but instead, today, I just want to play a game with you. So there's a game called Patience, and let me go over the rules with you, just a few rules. So sort of like solitaire where you have piles of cards, there's piles in the game, and so initially there are no piles of cards. The first card dealt forms a new pile consisting of the single card. From then on, every subsequent card dealt is placed on the leftmost existing pile, whose top card has a value greater than or equal to the new card's value, or to the right of all the existing piles, forming a new pile. What this is going to do is the top card that's facing up will form a sorted sequence, like the top visible card. From left to right, it'll be sorted. And also the piles themselves will be sorted from bottom to top. So it's sort of like a sorting algorithm, but being done incrementally. Like you're not sorting the whole thing at once, you're sorting it portion by portion, and you'll see what I mean here as we demonstrate it. So originally I wanted to, use my tech skills to show you a video of me sorting these cards, but I'm not that tech savvy, so we're gonna have to go to another window here. All right, so here I have a virtual poker table and some deck of cards. So let's play the game, right? So the first card dealt creates its own pile. From then on, you take the new card and insert it to the leftmost pile with a number greater than or equal to its value. All right, so I'm going to say aces are high, so ace is going to create its own pile. Now I have a 6. 6 is going to go to the leftmost pile with a number greater than or equal to 6. And it's going to go on top of this ace. Quick thought here, right? I have a sequence right now that goes 4 and then 6. So this might have something to do with our solution. All right, so now I have a 3. It's going to go to the leftmost pile. I have a 5. Leftmost pile with a number greater than or equal to 5. I have a 4. The insertion point is going to be here. Okay. I have a value that has to create a new pile. There's no card here greater than or equal to Jack that's on the front of the front of the pile. The 8's gonna go here to create a new pile with this queen. Leftmost pile with a number greater than or equal to 8 is this one. Okay, so I'm going to stop here because this will go on and on for 52 cards and you'll get bored and run away. But what I want to point out here is that these piles, each one is sorted. You can see like 4, then 3, ace, 6, 5, 4, jack, 8, 8, 8, queen, queen, 9, king. So all of these piles are sorted individually. And then also from left to right, they are sorted. The top card is sorted. 3, 4, 8, 9, king, that's sorted. So this algorithm, or this game is an algorithm for sorting. It's called patience sort. So like, take a look at this next card, 5. Where can I put it? I can actually do a binary search on the top facing card and find the insertion point. So I'd start at the middle. 8 would work as an insertion point. Can check left or right in this case, and neither of those are valid, so 5 would go on top of the 8 here. So you can do a binary search for the insertion point, and then once you have all the cards dealt, you'll have a certain number of piles. At that point, you can merge all of those sorted lists together to create an overall sorted array. And you would do that with like a priority queue, similar to if you ever saw the problem merge k-sorted lists. You would pick off the smallest card from each pile, 3, 4, 4, 5, 5. Right, I'm doing a k-way merge. 6, 8, 9. Okay, so now why do we care about this game? So the reason we care about this game for this specific problem is because it directly solves the longest increasing subsequence problem. So let's try again. I'm going to go quicker this time. So I have a 10. This is the first number in my sequence. I have a 9. Okay, this goes here. I have a 2. This can go here. The 3, this has to go here. Okay, when I created this new pile, I actually found a new maximal increasing subsequence. 2 and 3 creates an increasing subsequence of length 2. Look at the next card, it's a king. That can't be placed on any of the leftmost piles, any of the left piles. King goes here, it's a new pile. I found a new maximal increasing subsequence of length 3. 10. This can go here. So this one did not increase the length of the longest increasing subsequence. It is an alternate though, right? 2, 3, 10 is an alternate solution. Okay, queen. This creates a new longest increasing subsequence. 2, 3, 10, queen. So you can go on and on playing this game until you've gone through all of the elements in your array or the cards in your deck, and you will find that the length of the longest increasing subsequence is equivalent to the number of piles you make when you're playing patience. So thank you for your patience listening to me on this one. So what did we just do? We partially sorted the input, right? Because we didn't even need to merge those piles into one to completely sort it. We just partially sort the input, and that yielded the solution to the LIS problem. And then optionally, we can merge the k-sorted list if we're doing patient sort. But in this LeetCode problem, we just want to solve LIS, so we don't have to do that. Victory is ours. The code is in the description. Please remember to like and subscribe. Wrapping it up here, I think I just have one point. Even seemingly obscure algorithms like patience sort can sometimes, have their place in solving problems. And I just think it's really cool that you can find new ways to solve problems, right? Like just because a problem is classified as dynamic programming doesn't mean that you have to use dynamic programming to solve it. There might be other more efficient ways or simpler ways. So I hope you like this video. I thought it was really cool to learn about how a card game inspired a sorting algorithm. And I think it would be cool to like keep this one in your back pocket in case you ever get the LIS question in an interview, because you can sort of talk through how you can do this in n log n time. Yeah, so hope you like this video. Sign off this week and have a great rest of the month. Take care.